All right. So this will be the review for the Unit 1 exam. It starts 6 p.m. tomorrow, Monday, February 21st, and closes 24 hours later, Tuesday, February 22nd at 6 p.m. There's also an extra credit assignment. I forgot to mention that in the email earlier. And that will close on February 22nd at the same time that the exam closes. So really anytime between now and then, you just want to make sure to do that, because typically at the end of the semester, it's the people that just take the time to submit an entry for that extra credit assignment that end up doing a whole letter grade better than the people who just never bothered to do that. All of the extra credit assignments, the ones that are, kind of standard part of the course, that are part of each individual unit, are essentially one of the review questions that we go over in these videos. And then I just sort of pick one at random from the unit and make that the extra credit assignment question. So within this review, you'll have the answer to that as well. I'm going to go ahead and do a share screen thing and pull up the review questions for Unit 1. And if you want to, we can go over any of the material that was from the first test, the intro test, as well. I get a lot of warnings that I am presenting my screen. Yes, I know I'm presenting my screen. I can go over any of that, but I think I'm not going to repeat those answers from the review video that we did last time, because you can always go back and consult that. So, essentially I have a picture that is at the top of each individual unit, and you're not going to see this on the test specifically. I just pick a picture that is sort of representative of the unit as a whole. And in other versions of the class, when I have an in-person component, I'll have a test with this picture on it, but that's not going to be the case for you guys because you're doing this completely online. So a little bit further down, we've got Lecture 1 material, Lecture 2 material. If anybody wants to go over anything from those, just shout out to me anytime. I'd like to review this concept from this lecture, and I could certainly go over that. But we definitely did some of that with the first 3 review questions that we did in this video earlier. So the other thing that I want to go over is really just the rest of this unit that we haven't had a chance to go over and review yet. That's going to be laid out fairly nicely in the final 3 questions from the review question sheet. But, like everything else, if there's an individual question that you want to go over that's not part of those review questions, then, let's do that too. So essentially, when you're just trying to look for a comprehensive list of things to study for the exam, you want to go over the individual lecture outlines and just make sure that you've got notes from all of those individual topics. This is more of a, sort of just trying to get through all the details and look at the big picture and understand concepts. So that's what we're going to do today. So lectures 3, 4, and 5, and the review questions 4 through 6 that really emphasize those. Let me go back to the meet for a second, because I thought somebody had a question. Let's see. Yes. Can we review the intro exam if these are possible questions on the unit exam, please? That's a good question. You're not going to see any repeat questions, I don't think. I can go back and take a look at that. I do exam reviews, but I do them on a one-on-one basis. So if you want to go over that, then we need to come up with a time that we can meet. So I can probably make some time between now and the start of the exam tomorrow if you want to do that. Just send me an email and we'll figure out a time that works for both of us to review it. But like I said, you won't see the exact questions, but you might see similar questions. So going back to this review question document, this is actually laid out twice. No, like a human baby. Okay, I'm sorry. I should probably find a way to disable this for the purposes of reviews. I might have weird text messages coming through. I think a friend of mine does not want a puppy. She wants a human baby. It's a weird thing to come in, but that's fine. I'll tell her that later. She'll get a kick out of it. All right, so I blew this up a little bit, zoomed in a little bit. Like I said, from the review questions, and this is listed on the Moodle twice, once under the intro exam materials, and then the second time you have these review questions at the end, so you can find them in both of those places. We already did the first 3 questions because these are concepts from the first 2 lectures that were part of the intro exam. So 1, describe the major mechanisms. That's internal and external heat. Internal heat driving tectonic activity, volcanoes, mountains, earthquakes, all that kind of stuff. External heat being heat from the sun, driving weather, driving the erosion of the surface. 2, describe the 3 basic types of plate boundaries: divergent, transform, and convergent, and all of the different features that form as a result of those plate boundaries. So again, things like mountains, volcanoes, earthquakes, so on. And then 3, what are the 3 major types of faults? Reverse, normal, and strike slip. They relate to the 3 different types of stress: compressive stress for reverse faults, tensional stress for normal faults, and shear stress for strike slip faults. And all have a different resultant sort of expression in how they either extend, elongate the crust, or shorten the crust. So that's gone over really thoroughly in the other review video. If you didn't get a chance to watch that before you took the intro exam, it might be worth going back and looking at sort of a more detailed answer to those 3 questions. But what we're going to do today is mainly concentrate on 4. All right. What are the 2 types of body waves, and how do we use those waves to study the interior of the Earth? Okay, so note that first off, this question is only referring to body waves, and body waves are just one type of seismic wave. So in lecture 3, where I cover earthquakes, I go over all of the different types of seismic waves. And seismic waves can be broken down into surface waves, which are Rayleigh and Love waves. They travel at about the same speed, and they're doing most of the damage during an earthquake. But they actually travel a lot slower than waves that stay underground, that are just moving through the solid interior of the Earth, and they're not effectively riding this boundary between the solid Earth below and the air above. And that's body waves. The 2 different types of body waves are P for primary waves and S for secondary waves. As the names would suggest, primary waves travel faster. And the other major distinction is that they have a effectively, they have the ability to travel through all kinds of different medium. They can travel through solids, liquids, and gases. And then the last distinction that I'm not going to list out here is that they're a compressional wave. And so in the lecture videos, I described these with a slinky, and you actually have the slinky like shortening, like, you know, crunching back in on itself and then pulling outward. And then that's what the wave itself is doing, is it travels through a medium. You know, so we'll say that the type of material that this primary wave is traveling through is rock. At a molecular level, the rock itself is actually compressing and expanding as the wave's traveling through it. And it's traveling pretty fast, faster for really, really dense forms of rock, and then not quite as fast for less dense forms of rock. Okay, so second part of this down here, secondary waves are slower. So when you think about their arrival at a seismic recording station, because they're slower, they're always going to come in later. And that difference between when the P wave arrives and when the S wave arrives gives you an indication of how far away the earthquake happened. That's the PS separation, or PS arrival time distinction. So the slower wave can only travel through solids. Now, the second part of this question, first, what are the two different types of body waves? We described that. Second, how do we use those waves to study the interior of the Earth? So we talked about this a little bit already, but the velocity, which is just speed with a direction, of both waves gives us an indicator of the density and type of material the wave is traveling through. And so, for instance, we know that the deeper interior of the Earth is made out of a heavier, denser form of rock than the outer layers of the Earth. The upper mantle and then the crust are going to be made up of comparatively lighter forms of rock than the lower parts of the mantle, and definitely the core, and we know this because of the speed in which these waves travel. Second part of this, the inability of S waves to travel through liquids tells us where there are non-liquid areas in the mantle, or non-solid areas in the mantle. Molten rock exists. The last part of this is that the inability of S waves to travel through the outer core. So once they go through the mantle and they've reached the outer core, we know the outer core is in a liquid state because S waves can't travel through the outer core. And this results in a big sort of shadow in the surface expression of these waves after they travel through the interior of the Earth and once they come out the other side on Earth. So effectively, the seismic waves, particularly the body waves, tell us as much information as really anything can about the Earth's interior. Otherwise, it's essentially impossible for us to study the Earth's interior directly. So we have to count on these sort of more indirect methods of scientific determination to try to get at any kind of like reasonable information about the Earth's interior. So all of this was gone over in much more detail in both lectures 3. That's where I kind of go into the difference between the P and the S waves. And then lecture 4, that's where we go into the different parts of the Earth's interior and what these waves tell us. But just as a kind of quick sum up answer for these review questions, that's effectively what I'm looking for. Let me bounce back over for a minute over to the meet. And it doesn't look like anybody has any questions right here. So I'll go back to more of these review questions. The next one actually takes us all the way to lecture 5. It's kind of like this one question is from lectures 3 and 4. So of these remaining questions, I think this one is the sort of the heaviest, the one that is going over the most information from the lecture videos. 5, how did the dominant thinking in the geological community shift from not accepting Wegener's continental drift hypothesis to an eventual acceptance of plate tectonics 50 years later? Why was the originally correct idea initially discredited but later accepted? So to understand this, you need to first understand that in 1912, Alfred Wegener, it's actually should be spelled that way in the question, my bad, proposes the continental drift hypothesis based on the puzzle-like fit of continents on either side of the Atlantic Ocean. Strange fossil distributions of non-marine fossils on non-adjacent continents. So effectively the same sort of creatures, their remains found on different continents, whereas you get distinct speciation in modern animals today. And like the New World versus the Old World, the animals on, Australia being very different than Asia and so on. You get these matching fossil distributions on non-adjacent continents. So the theory being, if you put those continents back together, that makes a lot more sense. They were freely roaming around that continent. And then the last little piece here is matching lava flows and glacial patterns. Okay, so he comes up with a pretty decent working hypothesis. Effectively, I can explain all of this weird stuff by saying that at some point in the past, the continents were actually one big continent, and he coined the name that we give to the most recent supercontinent, and that's Pangaea. The problem with this is that nowhere in all of this explanation does he include some sort of driving force that's making these continents move. So he didn't come up with any sort of idea of why they had shifted from their hypothetical point at some point in the past where they were all together to the modern distribution of continents now where they're spread across the globe. So 50 years later, that piece of the puzzle was put in and it becomes a lot more accepted. Harry Hess, in post-World War II America, comes up with this sort of the very, very earliest stages of sort of what we call the plate tectonics theory. He proposes seafloor spreading as a mechanism that drives continental drift / plate tectonics. So effectively, this is just a mechanism that Wegener could never have come up with because at that point, so little was known about the seafloor. But after World War II, after all of the mapping on the seafloor, we have a better idea of what could actually be driving the continents to actually be in motion. And it's more like the continents themselves are not really in motion. They're being pushed and pulled apart by the creation and destruction of the seafloor. So that's why it's called seafloor spreading. This provides a rationale for why the continents were able to move, which was not included in Wegener's original hypothesis. So effectively, that's almost all there is to it. You have the separation of 50 years, which seems like a lot, and it seems really trivial that Wegener basically had the right idea, and then later on someone else got the acceptance for that being an accurate idea. But that missing piece was really, really important in changing the minds of people, especially considering that Wegener was not a geologist. His branch of science was so very unrelated to the people that were working on geology at the time. So it's already sort of a steep ladder for him to climb to be able to make some grand pronouncement that was going to change all of geology. And it took a little bit more than what he was able to provide to actually convince people. And most of all, it took an actual driving force to convince people. So this was covered in a lot of detail in lecture 5, in addition to a whole lot of other information on sort of this problem of continuing to prove plate tectonics over the 60s and over the 70s, and lots of other scientists jumping on board and including these different things that hadn't really been considered and factored in before. Okay, so that basically sums us up on question 5 right here. I'm going to go back over to the chat again, make sure. I think I'm getting a little noise when, yeah, because I heard it earlier, when I am getting a, someone typing. So I think I'll know when to be able to go back and make sure that happens. So we'll go up to 6 here, and then we'll see what else there is to go through and review and get you guys ready for this exam this week. The last question is coming from the very end of lecture 5. So in lecture 5, I really kind of go through a couple of book chapters. I mainly stick around on, I think, chapter 17. That's the general plate tectonics chapter. And I go forward a couple of chapters to, I want to say 19, and that one is all about mountains. But I only really cover this over the span of maybe 10, 15 minutes at the end of lecture 5. It's just a little bit about the basic timeline in mountains, why they're important, how they form, how they're related to the plate tectonic cycle. So I wanted to do a little extra on that. So in more the lecture and not so much the book, I have a different way of explaining this than the book does. I go through 3 steps in the evolution and eventual destruction of mountain belts. So let's, it does not like how I'm doing this. Okay, there. All right, well, we'll do it this way. I'm going to go through 1, 2, 3, these 3 steps that I'm asking about in the evolution of mountain belts. The first being, I think what I call in the notes, the intense deformation stage. In order for mountains to eventually form, the first thing that has to happen is the collision of 2 pieces of crust at a convergent plate boundary. So you cannot have mountains forming at all effectively without some form of convergent plate boundary taking place, existing, evolving over time. So what this does is whenever you have either continental convergence or continental oceanic convergence, leads to mountain formation. So the basic sense of motion here is that whatever's happening, you have to have 2 pieces of crust moving towards each other. This eventually leads to mountain formation by thickening the crust due to geologic structures, due to the formation of geologic structures that accommodate compressional stress. And those are things like thrust faults and folds. So effectively what's happening here, whether you have continental convergence, which is really ideal because then you have 2 pieces of crust to crumple up and to compress and thicken, or you have continental oceanic convergence where you have subduction of one plate, the oceanic plate, underneath the continent, but then the continent's crumpling up a little bit. Either way, you're thickening up the crust, you're shortening it in the horizontal dimension, you're thickening it in the vertical dimension. And you're doing this by continuing to push those plates further and further together, creating compressional stress. And then the compressional stress releases itself, in a sense, by creating thrust faults up closer to the surface in the shallower part of the crust. And then deeper, the material is ductile enough to bend instead of break, and then you get folds. So we call these fold and thrust belts. And that's a pretty classic set of geologic structures that form in the early stages of mountain formation. So the second part of this whole story, no, it doesn't like when I do that. Okay, fine. Automatic numbering is my nemesis in Microsoft Word. Part 2 of all of this is when the mountains actually start to rise significantly. You get most of your actual vertical uplift of mountains forming after most of the deformation has already taken place. So by crumpling up the crust, you've thickened it up a lot. But in order to make the mountains grow really, really tall, you get your tallest mountains in the world forming at this stage where the crust is already thickened, and then it starts to float up higher on the mantle. And this is a process that, to equilibrate this out and have all of this floating the right way on the mantle, it's not like a boat bouncing up out of the water. It's a process that takes millions of years. So this is called isostasy, and it's a fancy way of saying that something that's going to be thicker and weigh more, this has to actually float up higher on the mantle, because all of this crust, mainly all this continental crust, is really, really buoyant compared to the material that makes up the mantle. So in isostasy, the now thicker crust floats up higher on the mountain, on the mantle, sorry, which allows for most of the vertical uplift in mountain building. There are some geologic structures that are really important in this part of mountain belt formation, and that is block faulting. Block faulting, which is banded normal faults. Let's go banded high angle. Allow for some of this uplift to take place. So the first step in the evolution of mountain belts is that you have to crumple up the crust and make it thicker. The second is that that thicker crust has to then float up higher in the mantle. The third and final step, of course, has to be the eventual destruction of mountains by weathering and erosion. The slow processes of weathering and erosion destroy mountains over hundreds of millions of years and create stable continental cores in the aftermath. So the largest mountains on Earth will hundreds of millions of years from now either be much, much smaller mountains, sort of like the Appalachian Mountains, or they will eventually erode down to completely flat, stable, tectonic is the word we use to describe this, but stable continental cores. So this takes hundreds of millions of years as opposed to potentially maybe tens of millions of years for these initial stages in the evolution of mountain belts. So mountains, the whole mountain cycle is a process that takes even longer than the formation and destruction of oceans on Earth. This is a really, really long stage game in plate tectonics. Okay, so like I said, I covered this at the very end of lecture 5, but it's complicated, and it goes back into a little bit of the geologic structure material from the first 2 lectures. So I thought it might make a good review to kind of come full circle on some of this. So that's the last 3 questions from the review. Question 4 from lectures 3 and 4, 5 from the first half of lecture 5, 6 from the end of lecture 5. That's basically all I have to cover. So I think this might end up being sort of a short review, short video, unless you guys have more information that you want to talk about or go over. Does anybody have anything that they want to go through and review? Okay. What I'm going to do now is stop presenting. I'm going to stop the recording, maybe put you guys a little bit more at ease.